Explore the world of giant machinery in construction, mining, and engineering, and the assembly of these colossal heavy-duty trucks. Number 10 on the list is the Caterpillar D10T2. Although it first appeared decades ago, this iconic machine still represents strength from the past, combined with modern performance. Over the years, the D10T2 has undergone numerous technical upgrades, transforming it into a highly productive and versatile dozer. With an operating weight of about 70.17 tons, a powerful 766 horsepower engine, and a blade capacity of 18.5 cubic meters, it performs reliably on both heavy construction sites and demanding mining operations. At number 9 is the Tetra T40, the most powerful serially produced Russian bulldozer. Designed primarily for gold and coal mining, this machine weighs 70.28 tons and features a unique bogie-type undercarriage that provides superior traction in extremely rough terrain. Its 660 horsepower engine and massive 21 cubic meter blade ensure high efficiency while maintaining operator safety and comfort. Ranking 8th is the Shantui SD60C5, the second largest crawler dozer from the Chinese manufacturer Shantui. Weighing over 70 tons, this yellow giant is powered by a Cummins QSK-19 engine delivering 450 kilowatts. It features a semi-U blade with a capacity of 18.9 cubic meters and can be equipped with a heavy single-shank ripper for enhanced penetration in hard ground. Seventh place belongs to the Liebherr PR776 Electronic, a bulldozer known for its advanced technology and exceptional performance. With an operating weight of 73.18 tons and a 768 horsepower diesel engine, it excels in bulldozing, ripping, and grading. Its high blade penetration forces and precise control make it especially productive in heavy-duty mining applications. Number 6 is the Fiat Alice HD41, a historic machine that made headlines when it debuted in 1969. At the time, it was considered the largest bulldozer ever built. Weighing around 80 tons and powered by a 524 horsepower Cummins engine, it set new standards for size and capability in the early era of superdozers. In 5th place is the Shantui SD90C5, the largest mining bulldozer produced by Shantui. This massive machine weighs over 106 tons and delivers an impressive 962 horsepower using a Cummins QST30 engine. Its operator cab is designed for ergonomics, visibility, and noise reduction, ensuring comfort during long shifts. 4th on the list is the Komatsu D575A8, one of the most famous large crawler dozers in the world. Launched in 2020, it weighs more than 112 tons and produces up to 1040 horsepower, making it a cornerstone of large-scale earth-moving projects. At number 3 stands the Caterpillar D11TCD, the largest bulldozer ever built by Caterpillar. With an operating weight of 112.72 tons and a blade capacity of up to 43.6 cubic meters, it combines durability, efficiency, and long-term reliability. Second place goes to the Komatsu D575A 3SD, often called the Super Dozer. Weighing 152.6 tons and powered by an 150 horsepower engine, it is one of the most powerful production bulldozers ever made. Finally, the undisputed champion is the ACCO Super Bulldozer. Weighing an astonishing 183 tons and powered by 2 Caterpillar engines producing a combined 350 horsepower, it remains the largest bulldozer in the world, a true legend of heavy machinery engineering. The Komatsu 930E is a world-leading ultra-class rigid-frame mining dump truck designed to handle the most demanding large-scale mining operations. Renowned as one of the best-selling trucks in its class, the 930E combines massive payload capacity, proven reliability, and advanced diesel-electric technology to deliver exceptional productivity in open-pit mines around the world. With a payload rating of up to 320 short tons, or approximately 290 tons, the Komatsu 930E is built to move enormous volumes of material efficiently. At its core is a powerful Cummins SSDA16V160 diesel engine, producing up to 2 700 horsepower in the 930E5 model. This engine drives a diesel-electric powertrain with AC electric wheel motors, providing smooth acceleration, excellent traction, and reduced mechanical wear. Advanced technologies such as Invertex 2IE AC control, IGBT inverter technology, and Comtrax Plus monitoring systems enhance performance while simplifying maintenance and improving equipment availability. The truck can also be equipped with ComVision, offering operators improved visibility and job site awareness. Operator comfort and safety are prioritized through a modern, ergonomic cab designed to reduce fatigue during long shifts. With reinforced steel castings in high-stress areas, the Komatsu 930E stands as a flagship mining truck, delivering unmatched efficiency, durability, and long-term operational value. Komatsu continuous miners are heavy-duty machines designed for room and pillar mining in both coal and industrial mineral operations. Komatsu offers several proven series, including the 1-2 cm for high-seam mining, the 1-4 cm for low to mid-seam conditions, the robust 12 HM for industrial minerals, and the compact MC51 for hard rock applications. These machines focus on productivity, reliability, and safety. Optional Smart Zone proximity detection systems provide real-time awareness of nearby personnel, while remote operation allows operators to work from a safe distance. Integrated dust control, durable conveyor systems, and a multi-motor design further enhance performance and reduce downtime. Mining is a high-risk environment where many hazards must be carefully managed. One of the most dangerous hazards is the uncontrolled release of stored energy, particularly from the inflation of large haul truck tires. This scenario is based on a real accident that occurred on the 9th of February 2004 at the Century Zinc Mine, where a Komatsu 630E haul truck was involved in a catastrophic tire explosion. During maintenance work in the tire bay, residual pressure inside the wheel assembly caused a violent release of energy. The wheel was propelled at high speed, seriously injuring the truck driver and fatally trapping tire fitter Peter Marshall beneath the wheel. It is not intended to assign blame, but to respectfully remember those affected and to help the industry learn from past incidents. It highlights how inadequate control of tire pressure, limited exclusion zones, and insufficient training for rare but severe events can have tragic consequences. The reenacted rescue demonstration shows that effective response is not about speed, but about planning, coordination, and risk control. By understanding why these incidents occur and improving emergency preparedness, the mining industry can work toward its goal of ensuring every worker returns home safely each day. The Spider Crane URW295, manufactured by Furukawa UNIC, represents a new generation of compact lifting equipment designed specifically for work in confined and restricted environments. Combining advanced engineering with a highly flexible design, this mini crawler crane has become an essential solution for construction, industrial maintenance, glazing, mechanical installation, and indoor lifting operations where conventional cranes simply cannot operate. At first glance, the URW295 stands out due to its distinctive spider-like outrigger system. Unlike traditional cranes that require large setup areas, this crane uses multiple independently adjustable outriggers that can be deployed in a wide range of configurations. With up to 52 different outrigger positions, the URW295 can achieve outstanding stability even on uneven ground, narrow platforms, rooftops, stair landings, or sites filled with obstacles. This adaptability allows operators to safely lift loads in locations that would otherwise be inaccessible. One of the most impressive features of the Spider Crane URW295 is its compact size. With a travel width of just 24 inches, or 0.6 meters, the crane can easily pass through a standard single doorway and fit inside most service elevators. This makes it ideal for indoor projects, such as installing glass panels, HVAC systems, steel beams, or heavy machinery inside factories, shopping centers, or high-rise buildings. Once inside, the crane can be set up quickly and efficiently, without the need for structural modifications or dismantling walls. Despite its small footprint, the URW295 delivers remarkable lifting performance. It offers a maximum lifting capacity of 450 pounds at a radius of 4.6 feet, providing ample power for a wide range of tasks. The crane's telescopic main boom enables a maximum lifting height of 29 feet, which can be further extended to approximately 37 feet when equipped with a fixed hook or fly jib. This extended reach allows the crane to handle loads at height while maintaining precise control and stability. The working radius of the URW295 reaches up to 28 feet, giving operators the flexibility to position loads accurately, even in tight spaces. Whether lifting materials over obstacles, placing components through narrow openings, or performing delicate positioning tasks, the crane's smooth and responsive movements ensure efficiency and safety throughout the operation. Power versatility is another major advantage of the Spider Crane URW295. It is available in multiple power configurations, including gasoline, diesel, propane, and battery-powered models. This range of options allows the crane to be used both indoors and outdoors. In enclosed spaces, the battery or LPG versions provide low-emission or zero-emission operation, making them suitable for environmentally sensitive sites and areas with strict air quality requirements. Outdoors, the gasoline or diesel models deliver reliable performance in demanding conditions. Safety is a core focus in the design of the URW295. The crane is equipped with a safe load indicator system that continuously monitors lifting conditions. This intelligent system provides real-time feedback to the operator and includes a voice warning feature that alerts users when approaching load limits. In critical situations, the automatic stop function prevents unsafe movements and overloading, significantly reducing the risk of accidents. These safety features help ensure compliance with modern safety standards while protecting both operators and surrounding personnel. Control and ease of operation are further enhanced by the crane's wireless radio remote control system, which comes standard with the URW295. This remote control allows operators to manage all crane functions from a safe distance, providing a clear view of the load and the surrounding environment. In some applications, the operator can even control the crane from a man basket, enabling precise positioning during complex installation tasks. This level of control improves accuracy, reduces setup time, and enhances overall job site safety. In conclusion, the Spider Crane URW295 is a highly versatile and powerful mini-crawler crane that redefines what compact lifting equipment can achieve. Its combination of narrow access capability, impressive lifting capacity, flexible outrigger configurations, multiple power options, and advanced safety systems makes it an ideal solution for modern construction and industrial projects. Whether operating indoors, outdoors, on uneven terrain, or in extremely confined spaces, the URW295 delivers reliability, precision, and performance where larger cranes cannot go. The hydraulic container tilter, also known as a container turnover machine, is a powerful material handling solution designed to tilt shipping containers for fast and controlled bulk loading or unloading. Built with heavy-duty steel and driven by a full hydraulic system, the machine delivers smooth, stable, and reliable rotation even when handling fully loaded containers. One of its main advantages is efficiency. By tilting the container at a controlled angle, bulk materials such as grains, minerals, or scrap can be discharged quickly, reducing packing or unpacking time by 2 to 3 times compared to manual methods. Operation can be managed by a single operator, often using remote control, which significantly lowers labor requirements. Safety is a key focus, with features such as velocity fuses and robust structural design to prevent sudden movement. The system is versatile and available for both 20-foot and 40-foot containers, making it ideal for ports, warehouses, and industrial facilities. The Isuzu truck assembly process begins with stamped steel sheets that are precisely formed into individual body panels. These panels are transferred to automated welding lines, where robotic systems assemble and weld the cabin structure with high accuracy and consistency. Once welding is completed, the cabin frame moves to the painting line. Here it undergoes surface cleaning, anti-corrosion treatment, primer coating, color painting, and final baking to ensure durability, uniform finish, and long-term protection against corrosion. After painting, the cabin enters the comprehensive assembly stage. Doors are assembled separately, starting with the installation of window glass, door locks, hinges, and waterproof rubber seals. Once completed, the doors are carefully mounted onto the painted cabin body and adjusted to ensure proper alignment and sealing. Next, interior assembly begins in a step-by-step sequence. Electrical wiring harnesses are routed throughout the cabin, followed by the installation of insulation materials for noise and heat reduction. The dashboard module is then fitted, along with the instrument cluster and control interfaces. Seats, pedals, steering components, and other control systems are installed to complete the driver's operating environment. Following the interior work, exterior components are assembled. Side mirrors, headlights, signal lamps, grills, and decorative panels are mounted to the cabin, enhancing both functionality and appearance. Each component is checked for correct positioning and secure fastening. The assembled cabin is then mated with the chassis. The engine is installed into the front section, connected to the transmission and supporting systems. After that, axles and wheels are mounted, completing the main mechanical assembly. Finally, the finished truck undergoes a series of inspections and functional tests. These include checks of mechanical systems, electrical functions, sealing performance, and overall assembly quality to ensure the vehicle meets Isuzu's production standards before completion. The assembly process of an American truck tractor begins with chassis assembly, which forms the structural backbone of the vehicle. Heavy-duty longitudinal frame rails are positioned on precision fixtures to ensure correct alignment. Cross members are installed and bolted or riveted to reinforce rigidity and torsional strength. Suspension components, including front axles, rear drive axles, springs, airbags, and shock absorbers, are mounted directly onto the chassis. Brake systems, air lines, and steering linkages are then installed, creating a rolling frame capable of supporting the full drivetrain and cab structure. Once the basic chassis is assembled, computerized control processes are used to manage and monitor every critical operation. Manufacturing execution systems track each truck's build configuration, torque values, component serial numbers, and assembly sequence. Automated torque tools are digitally controlled to ensure that fasteners meet exact specifications. Real-time data collection allows operators to verify that every step is completed correctly and consistently, reducing human error and improving overall build accuracy. The process then advances to robotic cab assembly, where cab components are joined using automated robotic systems. Stamped steel panels, including the floor, side walls, roof, and rear wall, are positioned by robots with high repeatability. Robotic welding arms perform hundreds of welds with precise heat control, ensuring consistent weld penetration and structural integrity. This automated process improves strength, reduces distortion, and guarantees uniform quality across all cabs. Following welding, laser tolerance verification is performed to confirm dimensional accuracy. Laser scanners measure critical points on the cab and chassis, comparing them against digital design models. Any deviation beyond allowable tolerances is immediately detected and corrected. This step ensures that body panels will align correctly, doors will seal properly, and downstream assembly operations can proceed without fitment issues. With dimensional accuracy confirmed, precision fuel tank welding begins. Aluminum or steel fuel tanks are fabricated using controlled welding processes to ensure leak-free seams. Automated welding systems maintain consistent bead profiles and penetration depth, while pressure testing verifies tank integrity. Mounting brackets and protective shields are then attached, preparing the tanks for installation on the chassis. The assembled cab moves through automated paint systems, where surface preparation begins with cleaning, degreasing, and corrosion-resistant pre-treatment. Electrodeposition coating is applied to provide uniform coverage and long-term rust protection. The cab then enters robotic paint booths, where multiple layers of primer, base coat, and clear coat are sprayed under controlled temperature and humidity conditions. Robots ensure even paint thickness and flawless surface quality. After painting, the cab is cured in temperature-controlled ovens. After curing, the cab proceeds to MX-13 engine installation. The PACCAR MX-13 engine is pre-assembled and tested before being delivered to the line. Using overhead cranes and guided fixtures, the engine is carefully lowered into position within the chassis. It is securely mounted and connected to the transmission, driveline, exhaust system, and engine mounts. Fuel, cooling, lubrication, and electronic control connections are completed with strict torque and routing specifications. Next, the painted cab is married to the chassis, followed by cab quality verification. Inspectors examine door alignment, hinge operation, ceiling surfaces, and interior fitment. Windshield and side windows are checked for proper installation and sealing. Interior components, such as seats, dashboards, trim panels, and insulation, are inspected to ensure correct installation and finish quality. Any defects identified at this stage are corrected immediately before further testing. The truck then enters the engine test laboratory, where the powertrain is evaluated under controlled conditions. The engine is started and run through various operating ranges to verify performance, fuel delivery, emissions systems, and electronic controls. Sensors monitor vibration, temperature, pressure, and noise levels. This testing confirms that the engine operates within specified parameters before the vehicle proceeds to dynamic testing. After engine testing, the vehicle moves to the electrical laboratory. All electrical systems are systematically tested, including lighting, instrumentation, infotainment, driver assistance systems, and control modules. Diagnostic tools communicate with onboard computers to verify software calibration, fault codes, and signal integrity. Wiring harnesses and connectors are inspected to ensure proper routing and secure connections. The next stage is the cooling cell, where the truck is subjected to simulated operating conditions to evaluate thermal performance. The engine and cooling system are run under varying loads to ensure that coolant flow, radiator efficiency, and fan operation maintain proper temperatures. This testing confirms that the truck can operate reliably in high-demand environments without overheating. Once thermal performance is verified, the truck proceeds to the durability track. This controlled test course simulates real-world driving conditions, including uneven surfaces, sharp turns, braking events. Following track testing, the truck undergoes evaluation in the structural laboratory. Selected vehicles or components are subjected to structural analysis, including load testing and stress evaluation. This laboratory verifies frame strength, cab integrity, and component fatigue resistance. Data from these tests is used to validate design assumptions and improve long-term reliability. After completing all laboratory and track evaluations, the truck returns to the final inspection area, where all test results are reviewed and verified. Any required adjustments or corrections are performed before the vehicle is approved for completion. The finished American truck tractor meets strict quality, performance, and durability standards through this highly controlled and systematic assembly process. A Malaysian Armed Forces Iveco Euro Tracker 6x6 tank transporter carrying an ACV 300 Adnan IFV halted on the LPT highway due to engine trouble. The process begins by loosening the tire bead from the wheel, while always assuming that a TPMS sensor is installed. The wheel is positioned so the TPMS sensor is at the 12 o'clock position, allowing the operator to clearly identify and protect it throughout the procedure. The tire is rolled into the bead braking pad and the shovel is carefully aligned against the sidewall. Pressure is applied just enough to break the upper bead loose without excessive force. Only a small separation is required at this stage. Next, the wheel is turned over so the backside rests against the pad. The TPMS sensor is again positioned at the top. The shovel is brought in gradually to loosen the lower bead, taking care not to fully collapse it against the pad to avoid damaging the sensor. The wheel is rotated incrementally, repeating the bead braking action until the bead is completely free from the rim. Once both beads are loosened, the assembly is moved to the tabletop of the tire changer. The wheel and tire assembly is placed on the tabletop, with the inner diameter facing the expanding clamps. The clamps are expanded to securely grip the wheel from the inside, ensuring stability during rotation. The operator verifies pedal functions for tower movement, clamp expansion, and table rotation. With the wheel firmly secured, attention shifts to removing the tire from the rim. The tower is positioned and adjusted so the duck head clears the wheel without contact. Plastic protectors on the duck head prevent scratching. The duck head is locked into position and the table is rotated. The upper swing arm is brought into place and locked to prevent unwanted movement. The bead is collapsed into the drop center, and mounting paste is applied to the upper bead to reduce friction during removal. Using the leverless hook, the operator inserts it into the gap created in the bead while the table rotates. The hook lifts the bead up and over the rim, staying clear of the TPMS sensor. A red spatula is inserted to hold the bead in position, maintaining a gap as the table continues rotating. This completes removal of the upper bead. The tire is then lifted and pulled toward the operator so the lower bead drops into the rim's drop center. The hook is reinserted to capture the lower bead, and the spatula is again used to guide the bead over the rim. Continued rotation fully removes the tire from the wheel. Once separated, the wheel is inspected to confirm the TPMS sensor remains intact and undamaged. Reassembly begins by placing the tire on the machine or floor rather than directly on the wheel to avoid cosmetic damage. Mounting paste is applied generously to the beads to prevent tearing during installation. The tower and duck head are returned to their preset position. The lower bead is guided over the duck head and positioned so part of the bead drops into the rim's drop center, keeping the TPMS sensor out of the bead path. The table is rotated while controlled pressure is applied, allowing the bead to slide smoothly onto the rim. The swing arm disc is positioned behind the TPMS sensor, so that downward force pushes the bead safely into the drop center without contacting the sensor. As the table rotates, the cam action of the swing arm automatically relieves pressure, allowing the bead to seat correctly. The upper bead is then mounted using the same over and under technique, with constant attention to bead stress and TPMS location. Manual adjustments are made if excessive resistance is observed. After both beads are mounted, the swing arm and tower are moved out of the way. The valve stem is accessed, and the tire is inflated through the stem, with the valve core removed during initial inflation to speed the process. This completes the tire maintenance procedure while ensuring wheel integrity and TPMS protection.